Okay, we left few problems. Now you're going to notice I'm going to number the numbers slightly different. 22 prime, which means I'm going to change something minor in the problem. Two reasons. One, so that it's not really copying the book and putting that online. And secondly, so those will be accessible. I have to type those. When I'm cutting and pasting those, they're not coming out as a readable text for disabled students. So a minor change, so the numbers are going to match. If you look, the problem number 22 actually says the integral of e to the negative y cosine of y dy. So I'm going to change something minor in the problems and proceed. So here we look at this problem and we notice that, well, I can't eliminate this by taking enough derivatives or this. That is, you take a derivative of a trig function, you always get a trig function, and you take a derivative of an exponential, you always get an exponential. These type of problems, this is the third type of problems that we come across those. The first type is when you do integration by parts once. The second type is when you do integration by parts multiple times. You could use a shortcut. And here, you could use either. I'm going to show you how the book does this, and then I'm going to show you how the shortcut works on this. But there's a small catch to it. So you let u equal one of those. It doesn't matter which one. And dv equal the other. Whatever makes you happy. I'm going to work in a line. Normally we work downwards. In this case, I want to work in a line so you could see what we're doing. I'm going to choose u to be the sine of y because it seems it's easier for students to take a derivative of sine and cosine than integration. And dv would be the leftover. So somebody figured out if I do this twice, I'll get this back. So you just have to be patient when you do this and work slowly. And if I integrate, v will be negative e to the negative y, and this is going to equal u times v minus the integral of v du. So that's a negative becomes a positive, e to the negative y cosine of y. Now, negative e to the negative y is not a problem, but this integral right here, I'm going to do integration by parts on it again. And the reason for that, if you integrate sine twice, you get it back. If you integrate cosine twice, you get it back. If you take a derivative of sine twice, you get it back. And if you take integration of sine twice, you get it back. So either way. Oops, I messed up. There's a delta y, that's important. So when I integrate, I get v to be negative e to the negative y. And now, this integral right here is going to yield the product of those. So that's a negative e to the negative y cosine of y minus the integral of v du. Three negatives will keep it as a negative e to the negative y sine of y dy. Yeah, that's why I've been leaving those. There we go. Now, if I look at the far left, I notice it's repeating on the right. If I eliminate the part in between, if I ignore this part completely and just copy down what I'm seeing, I see this integral that I'm trying to find. And if I copy this far right, what's on the far right, I notice that there is, I think I messed up in the copying. Yeah, I did. There's a sign there, right? It's this term. There's a sign right there. There we go. So, I'm going to see a negative e to the negative y sine of y minus e to the negative y cosine of y. But now, I notice that this last piece is identical. And now if I use algebra, not calculus, if I move this to the right, wouldn't that be one of those plus one of those? That's two of those. And of course there's a plus c. You could add it in the beginning, you could add it at the end. That's not a problem. And this integral of e to the negative y sine of y dy would be negative 1/2 e to the negative y sine of y minus 1/2 e to the negative y cosine of y plus, You could write c over 2 if you wish, but that's the answer. So this requires me to do an equation by parts twice. Now, the shortcut does work on this, but there's a small modification you would have to do. That is, if I was to follow the trend, if I was to let u equal like it shows, sine of y, a derivative of that would be cosine of y, and a derivative of that would be negative sine of y. If I let dv equal e to the negative y, negative e to the negative y, e to the negative y, and this is the catch. When I work this out, remember you start with a plus and then a minus. So I could say the integral of e to the negative y sine of y dy is going to equal the product of those minus the product of those. And since I'm not getting a 0 right there, I'm going to stop. Well, this is the catch for stopping. Anytime you want to stop, you integrate that piece. So minus the integral of anywhere you want to stop. That works all the time. And you notice you are at this stage. You cut yourself this step and this step. And then you could proceed and finish the problem like you just did. So you want to use the shortcut, good for you. You want to use integration by parts, that works as well. Let me get the next problem in. I'm looking at number 24 prime. Again, I changed something in it. It was a sine of 2x. I made a cosine of 2x. So let me do this both ways as well. Again, if I let u equal cosine of 2x and dv be e to the negative 2x dx. If I take a derivative, that's negative twice the sine of 2x dx. And if I integrate dv, I will get v to equal e to the negative 2x divided by negative 2. First step, you multiply those, negative e to the negative 2x divided by 2, the cosine of 2x, minus the integral of the product of those. 3 negatives will cancel out. That 3 negatives will keep at a negative. The 2's cancel out. So I'm left with e to the negative 2x sine of 2x dx. And now, my next step, this is going to equal negative e to the negative 2x over 2 cosine of 2x minus this integral right here. So if I look at what's going to come out of that, I let u equal the same deal, sine of 2x. du is twice the cosine of 2x dx. dv be the exponential part. And if I integrate, v will be e to the negative 2x divided by 2, negative 2. So this is going to be, again, this integral is going to give u times v. That's going to be negative 1/2 e to the negative 2x sine of 2x minus the integral of the product of those. 2 negatives will make it a positive, so the 2's cancel out. E to the negative 2x cosine of 2x dx. And now again, if I eliminate the middle portion, if I ignore this part, copy the far left, the integral of e to the negative 2x cosine of 2x dx equal, and if I copy this part, that's negative e to the negative 2x over 2 cosine of 2x plus 1/2 e to the negative 2x sine of 2x, and if I distribute that in, that's minus the integral of e to the negative 2x cosine of 2x dx. And the same trick as the previous problem, if I move this to the left, those come up to be 2. Again, whatever those coefficients are, sometimes it's 5, sometimes it's 1/4, whatever it is. So you're using algebra now, no longer calculus. I'm just copying down what I got. And I could say the integral of e to the negative 2x cosine of 2x dx is negative. Now the book, the author likes to write it this way. They factor a 1/4 out and an e to the negative 2x out. You don't have to do this. This is very important for differential equations. you really don't have to worry much about it here, and there's my answer. Of course, you could leave it as 1/4 e to the negative 2x cosine of 2x, and the usual. Or I could use the shortcut. I'm going to show you how that works again. So I could say, let's say u is the cosine of 2x right there. Derivative of that is negative twice the sine of 2x. A derivative of that is negative 4 the cosine of 2x. And I know I'm going to stop here because I'm going to do this only twice. dv will be the leftover e to the negative 2x. Integrate that, e to the negative 2x divided by negative 2. Integrate again, e to the negative 2x divided by 4. And remember, that takes a plus and that takes a minus. So the way it works here, I just gotta space this, right? So we don't lose track. So this is gonna equal this integral of e to the negative 2x cosine of 2x dx is gonna equal the product of those, that is negative 1/2 e to the negative 2x cosine of 2x. Here, negative times a negative will give me a positive, and when I multiply those out, that's going to be 1/2 e to the negative 2x sine of 2x. And since I am stopping right here, when I multiply those, that's going to be minus the integral. The first cancel out, e to the negative 2x cosine of 2x dx. And as you see, we eliminated a lot of steps, move this over, and proceed like we did the previous problem. So that's an important application. I'm going to give you a homework problem that applies to that, and you'll see how that works. A few more problems to do. Okay, you'll figure this out quickly. Radicals are very hard to maneuver around. I'll try a u-sub, it doesn't help. If I work this out, I have a couple of options. If I let u equal 1 plus x, du will be dx. And if you look at this, you say, well, that's the square root of what? U. And there's a dx that's du. But do you see I have an x left over? I could solve for x. Wouldn't x equal u minus 1? And why is this easier than what I started with? Because now I could say this is the integral, actually not 0 to 1, I'm going to talk about that in a minute. This is the integral of u to the 3/2 minus u to the 1/2. So initially I couldn't integrate, now I can by using the u-sub. Something you should really work on is change the limits of integration. If I put a 0 in for x, wouldn't u equal a 1? And if I put a 1 in for x, wouldn't u equal a 2? If I have a definite integral, which means I have the limits on the integral, I could change the limit from dx du and never go back. And that's worth doing because we're going to be integrating in multiple steps. That saves you a few steps on the long run. And wouldn't this be u add 1 to the power divide by that, add 1 to the power divide by that, evaluated from 1 to 2, that will be 2/5 times 2 to the 5/2 minus 2/3 2 to the 3/2 minus 2/5 minus 2/3, and on a test, that's all you need. And there's my final answer. There are a couple of ways I could have did this problem. This is one of them. Next problem up, number 38 prime. Again, equivalent to number 38. If it's not the same, it's very close. So if I here look at this and say let u equal the exponent, x cubed. By taking a derivative, I notice that's 3x squared dx. When I'm glancing at this, if I fill in the blanks, I'm going to rewrite this because it seems I need the x. To get the x, I'm going to take this and write it as x squared dx. That leaves me with x cubed e to the x cubed. Now if I fill in the blanks, that is, if I take this out of the equation first, I could do that. Off by a constant is a small price to pay. That's simply du. And if I let u equal x cubed, it seems that's going to happen in two places. I'm going to have a u and e to the u. Now, you could think of this as the integral of x e to the x, integration by parts once and I'm done. I know it's kind of annoying, but you could let u equal, if this was the integral of x e to the x dx, wouldn't you let u equal x? You could let u equal u, or you could use a different variable. And dv will be what? Whatever's left over, e to the u du. That is doable. A bit annoying in the beginning, but you could adjust quickly. And this is going to be 1/3 times u times v minus the integral of v du. And that's going to be 1/3. And what was u? U was my x cubed right there. So that's going to be x cubed e to the x cubed minus, and isn't the integral of e to the u e to the u? And don't forget the plus c. And that would be my final answer. And the last problem I'd like to look at is number 46 prime. Again, very close to it. Well, here, if I proceed and let u equal the radical y. Now, I am aware if I take a derivative of this, I'll get 1 over twice square root of y, but I don't have that. So I think of du before I go. I could square both sides to really get a delta y. I could say u squared equal y, and now if I take a derivative, I could say dy is simply 2u du. And what that means, this is going to become the integral, and just so that I wouldn't lose track, I start with delta y first. That is 2u du. And then, if I replace square root of y by u, I'm really looking at u e to the u. And doesn't this become really twice the integral of u squared e to the u du? And I know the drill. If I had the integral of x squared e to the x dx, I know by now that I should have used integration by parts twice. So you proceed the same way. You could use the shortcut. Let u equal what? U squared, a derivative of that, and dv be e to the u. You want to use a different letter, you're welcome to. It really makes no difference. Easier to get used to it this way. A plus, a minus, and a plus. So this is going to equal 2 times the product of those, u squared e to the u, minus 2u e to the u, plus 2e to the u plus c, and that would be twice. Remember what u was. U was radical x. So that's going to be square root of x squared is y e to the radical y minus twice square root of y e to the radical y plus e to the radical y. And of course, if you factor e out of those, the problem will look a lot nicer. And this would be the rest of the homework for this section, and that concludes 8.1.